Okay, so here's a note on this idea of doing PEMDAS in reverse, working backwards, or doing those inverse operations to work backwards to find what the true value of a variable is in an equation. So let's say that we have x plus 9 equals 20. Okay, so as we go along here, this is a plus, so we need to do the inverse operation of addition, which is subtraction. But I need to do it to both sides. So that's x equals 11. Okay, so x equals 11. So that's a correct solution, because if I plug 11 back in for x, 11 plus 9 indeed equals 20. It creates an identity, 20 equals 20. Okay, so the question is, when there are several operations that we need to do, which one do we sort of do the inverse of first? So let's pick another number. Let's do 8 here. X plus 8 equals 20. How about this? 2x plus 8 equals 20. So the question is, what do we do first? Do we take away 8 from both sides, or do we divide 2x by 2 and 20 by 2? So here is the thing. I highly suggest that, you know how there's PEMDAS, which is parentheses, exponents, multiplication and division, they're kind of a package, and then addition and subtraction, those are kind of like a package. So in PEMDAS, when we're working forwards, we get to multiplication or division first, and then we do addition or subtraction second. Well, remember, when we're doing when we're solving for equations, we're doing the reverse, everything backwards, like all backwards, right? It's like playing a tape or a video backwards to see what this originally was. So instead of doing PEMDAS forwards, think of doing PEMDAS backwards. So we're actually going to do our additions and subtractions first, and then do our divisions and multiplications second, backwards. Okay, so instead of doing multiplication or division first, let's do the addition and subtraction first, okay? Because we're doing it in reversed order. So I'm going to take away 8 from both sides first. So that leaves us with 2x equals 20 minus 8 is 12. And then I'm going to do the inverse operation of multiplication, which is division. As long as I divide both sides by the same number, I'm okay. So 2 divided by 2 cancels out to 1 over 1. 1x, a positive 1x, truly is isolated. And 12 divided by 2 is 6. Okay? So now let's just plug back in, substitute, just to confirm that this is indeed the correct solution. Remember, a solution creates an identity if it's an accurate solution. So let's see what happens. We're going to plug 6 back in for x. See what happens. 2 times 6 plus 8 equals 20. Okay, now, since we're evaluating, we're just doing the arithmetic. We're not solving for anything. We're actually trying to do the arithmetic to see if this is true. Now we do PEMDAS forwards. We do it just like we were given any numerical expression, like just evaluating numerical expression. We use PEMDAS. So here we're going to do multiplication first now. 2 times 6 is 12. 12 plus 8. And 12 plus 8 is 20. 20 equals 20. This is an identity. You have the left and the right-hand side looking exactly equal to each other. And so solutions make identities out of equations. And 6 indeed was the key to this equations lock. Okay, now I'd also like to say something about equivalent expressions. Okay, so we talked a little bit about these concepts of having the left-hand side and the right-hand side look exactly the same. Okay, so let's sort of take that idea to try to see if we can come up with something that equals this exactly. Okay, so an identity equation is where the left-hand side and the right-hand side are equal from the very start. let me show you how. Okay, so do you see that 2 times in parentheses x plus 5? This would be a perfectly good expression, okay? And what we can do is we can distribute the 2 over everything inside the parentheses. When we distribute over everything in parentheses, we call that expanding. Expanding, okay? So it's called expanding this expression. So let's make this expression expanded into an equivalent expression, meaning an expression that means the exact same thing. Okay, so let's go. 2 times x is 2x plus 2 times 5 is 10. So we just expanded this to be that, okay? Because we, if you want to make that 10 like 2 times 5, to make it even clearer, do you see how we expanded this 2 over everything in the parentheses? Okay, so these are equivalent expressions. This is an equivalent expression of that, because when we expand over everything in the parentheses, what we're doing basically is getting all the guts of the that's inside the parentheses, and we're kind of drawing them out a little bit longer, but it's still the same amount of material at the end of the day. It's the same thing, okay? Just expressed in a different manner, okay? But they truly are equivalents, okay? So what we're trying to do is, through expansion or factoring, look at this. Do you see that when we went from here to here, we expanded the expression? What's the opposite of expanding? Factoring. Let's say that we had this expression first, and we wanted a factor. What is the greatest common factor that lives in both of these terms? 2. So what we could do is we could take 2, put it on the outside, and what are we left with in the parentheses? X plus 5. Look at that. They're the exact same. So this is the expanded form of this, and this is the factored form of that. So they are absolutely, absolutely equivalent. So this is, you know how I said when you plug a solution back into the equation, you come out with an identity at the bottom, like 15 equals 15? Let's see what happens when we put 2 equivalent expressions exactly equal to each other. I'd be interested to see what happens. Okay, so again, we could distribute that. So that's 2x plus 10 equals, and then this is also 2x plus 10. Okay, this is interesting. Subtract. So let's work backwards. So we're gonna subtract 10 from both sides. Get rid of the whatever you do on one side. Do the okay. So that's 2x equals 2x. Oh boy, this is interesting. And then now we're gonna divide both sides by 2. Whoa, that's even more interesting. And we have x equals x. X equals x. Well, that is certainly an identity if I've ever seen one. In fact, these aren't numbers that are identical. These are variables that are identical. This is a very interesting situation. When you have an expression, that equals an expanded version of the expression, what you're going to get is a situation where the variable equals itself. And if you ever get a variable equaling itself, this is a very special kind of equation, okay? And in this special kind of equation, there isn't just one solution. There are an infinite number of solutions. Isn't that interesting? So when you have a factored version on the left-hand side and the expanded version on the right-hand side, and you try to solve for x, you're going to come up with x equals x, or whatever the variable equals the variable. And what does that mean? You may think that you made a mistake, but you have not made a mistake. What you have stumbled upon is a very cool thing, and that means that x could be anything. So you would say all x if you want to say x equals all real numbers. Really? Any real number on the number line. It could be a positive number, it could be a negative number, it could be 0, it could be a fraction, it could be a decimal. It could be any real number, and it will always keep this these two sides balanced with each other. And I really do mean that. Like, let's try to plug in 0 here for x. So 0 plus 5 is 0. 5 times 2 is 10. Okay, so this side would be 10. 2 times 0 is 0. 0 plus 10 is 10. Okay, how about, I don't know, negative 3. I just picked that. Negative 3 plus 5 is 2. 2 times 2 is 4. Okay, negative 3 times 2 is negative 6. So this would be negative 6 plus 10. Oh, negative 6 plus 10 is 4. Oh, 4 equals 4. I literally could pick any number for x because this and this is the expanded version of this, so I could pick any number. And if you ever get a variable staring at itself, don't think that you made a mistake. Think that you just opened up the entire real, the real number line for anything. And that's, I think, a pretty cool thing. So just look out for that. And look out for trying to create equivalent expressions, okay? And one of those ways to create equivalent expressions is if you ever see a parentheses, try to distribute over it, and you'll create another version of something that's equal to itself. Here, I'll leave you with one last one. Let's pick something else like a. Okay, so let's say we had 0.5a, all right? And then we had a divided by 2, all right? So if I try to solve this, okay, boy, what could I do? I could do a lot of things. One thing is, do you see that there's 2 in the denominator? I want to get a by itself. So why don't I get a by itself by multiplying by 2 over 1? Oh, look at that. Do you see that these 2's now cancel to 1's? Because 2 is in the denominator, so if I multiply by 2 over 1, I get to cancel out. But remember, whatever I do to one side, I have to do to the other side, the do-do rule, or the property of equality, if you want to sound a little more appropriate for textbooks. Okay, so I multiply this side by 2, so I have to multiply this side by 2. Okay, what's 2 times 0.5, or what's 2 times a half, or what's 2 halves put together, 1 whole? So you get 1, so 2 times 0.5 is 1, so that's 1a. And then, whoa, I'm just left with 1a over here as well. Wait a second, a equals a. This must be one of those identities where the variable could literally be anything, and it will keep this equation balanced. And that is true, because multiplying, and if you go back, think about it. Let's go back to the original equation. If you are multiplying by a half, that's the same thing as dividing by 2. So multiplying by a half is so that's another way to you can see equivalent expressions set equal to each other that way. Anyway, I will leave you with that, and I'll see you in the next video.